Good morning everyone. Today I will tackle about orbits. So, what is an orbit? An orbit is a regular, repeating path that one object in space takes around another one. An object in the orbit is called a satellite. A satellite can be natural, like Earth or the Moon. Since the Earth orbits the Sun, you are actually in orbit right now. Many planets like Earth have moons that orbit them. A satellite can also be man-made, like the International Space Station. Planets, comets, asteroids, and other objects in the solar system orbit the Sun. What shape is an orbit? Orbits come different shapes. All orbits are elliptical, which means they are ellipsy, similar to an oval. For the planets, the orbits are almost circular. The orbits of comets have different shape. They look like a squashed circle. They look more like dense ellipses than circle. I have a video from YouTube on how objects stay in orbits.
Hey, welcome. Have you ever wondered why objects don't just crash into each other in space? So if you think about it, how does an object stay in orbit, like this satellite right here? Or you could ask, how are objects in orbit always falling and never hitting the Earth? So if you think about it, isn't it true that there is a force due to gravity on this satellite from the Earth? So we could say the force due to gravity on the satellite from the Earth, that is going to be the same as the force due to gravity on the Earth from the satellite because of Newton's third law. Now, this is largely insignificant because the mass of the Earth is just so great that the acceleration is basically nothing. But for this over here, that mass is relatively small compared to the Earth, so it does have a larger acceleration. So you could say, why doesn't this satellite accelerate into the Earth? What do you think? How are these things able to orbit each other and not crash into each other? And that's the question we're going to answer right now. In fact, back in 1687, Sir Isaac Newton wrote about this in a book that he published called the Principia. And one of the things he talked about, he said, imagine you have the world's largest mountain on top of the Earth. Now, this mountain here is not drawn to scale. And he said, imagine that there was the world's biggest cannon, like on top of the Earth. This is before there were missiles and so on. And again, this is clearly not to scale, but let's just roll with it for a minute because it's Newton talking here. And he said, now imagine the cannon fired a cannonball, and the cannonball went a great distance, maybe the width of like a continent or something like that, and it landed over here. As it was falling, you would think about the force due to gravity is going to be pulling it inwards. So we still have the force due to gravity. In fact, it's increasing slightly the closer it gets to the Earth, so the force due to gravity is actually getting stronger the closer to the surface of the Earth the cannonball gets. Now, that would be quite a cannonball shot because it would be very, very far over a great distance, like the width of a continent or something. All right, let's imagine that they supercharged the shot, so they put in even way more gunpowder. And again, some of this doesn't make sense, but just roll with it for now. So, cannonball supercharged, and boom, it shoots out, and over time what happens is this thing goes flying off. The force due to gravity, if we were to label that, should be pointing towards the center of the Earth, and that would actually get less and less because that drops off with an inverse squared relationship. So if you're a physical science student, just hang in there. If you're a physics student, I will mention this is Newton's universal law of gravitation down here. And so if your radius value, the distance between the center of both objects, increases, then the force decreases by an inverse squared amount. All right, now let's think for a moment. What if we launched the cannonball at just the right speed where it would fall at exactly the same rate that the Earth would curve out from underneath it? It would effectively be moving so fast in the x-axis when it was launched initially, and this is going to be our y-axis here, so fast in the x-axis that as the Earth curved out from underneath it in the y-axis, it would be staying at the same elevation. And then the cannon would have to be moved out of the way. But can you see where I'm going with this? The idea is that the cannon would be moving so fast in the x-axis that it would drop at the same rate that the Earth would be curving falling out from underneath it. And what that means is this cannonball would always be falling towards the Earth and never hitting it. And this is exactly how satellites work. These arrows represent the force due to gravity. Arrows towards the middle, force due to gravity, which is always pointing towards the center of the object. So you can have a circular motion for something, but that's exactly what's happening here for a satellite that's launched into orbit around the Earth. It's always falling towards the Earth and never hitting the Earth. And it has to be in an altitude where air resistance is not a factor, where it's above more or less the atmosphere of the Earth. However, if it gets too low and its orbit is too low and there is atmosphere up here, what can happen is over time it will start to sink down and eventually burn up, most likely in the atmosphere, or fall to the Earth. Alright, so hopefully that's helpful for understanding how something can be always falling towards the Earth and never hitting the Earth, or in other words, how something can always be in orbit flying around the Earth. And I'm going to end with one last question. I want you to think about, what is the Earth's natural satellite? Alright, thank you for listening. If you have any comments, let me know down below. And I'm going to continue with physics concepts throughout the entire year, so stick around for some more content.
The majority of satellites orbiting the Earth do so at altitudes between 160 and 2,000 kilometers. This orbital region is called low Earth orbit, or LEO, due to the satellites' relative closeness to the Earth. Satellites in LEO typically take between 90 minutes and 2 hours to complete one full orbit around the Earth. A satellite in polar orbit passes over the Earth poles, moving from the north to south or vice versa. As the Earth rotates beneath it, the satellite can eventually cover the entire planet. These orbits are typically lower, ranging from about 160 to 2,000 kilometers above the Earth. This orbit is much higher than a polar orbit, specifically about 35,786,000 kilometers above the Earth. Orbit type: polar orbit, passes over the Earth poles and covers the entire surface. Geostationary orbit, orbits above the equator, staying over the same point on Earth. Day altitude, polar orbit, lower around 160 to 1000 km. Geostationary orbit, much higher around 35,786 km.
So good day everyone. Today we're gonna tackle about the Kepler's law of planetary motion. Kanani, this is just the continuation sa report ni Aro. Is about the orbits and Kepler's law of planetary motion. For kani, so continuation na ni. So let's start. This is the history of Johannes Kepler. Johannes Kepler was a German astronomer and a mathematician of the late 16th and early 17th centuries. Kepler was born in Wittenberg, Germany in 1571. His parents were poor, but he was sent to the University of Tübingen on a scholarship in the recognition of his abilities in mathematics. Unlike Brahe, Kepler believed firmly in the Copernican system. In retrospect, the reason that the orbit of Mars was particularly difficult was that Copernicus had correctly placed the Sun at the center of the solar system, but had erred in assuming on the orbits of the planet to be circles. Thus, in the Copernican theory, epicycles were still required to explain the details of planetary motion. So, in the astronomy, Kepler's law gave a description of the motion of the planets around the Sun. Ang Kepler's law, nag-give siya og description sa mga motion gani or ang mga kung asa gani paingon ang dagan gani sa Sun ug ang planets nga nagpalibot sa Sun, kung asa dapit ila dagan ug asa dapit ila libot. So in Kepler's law of planetary motion, there are three laws. which is number 1, law of ellipses. Second law is the law of equal areas. The third law is law of harmonies. So I'm gonna show a video that explains these 3 laws, which stated by Johannes Kepler.
Hello learners, this is Easy Engineering. Today we're going to talk about another fun topic in physics. It is all about the Kepler's laws of planetary motion. Kepler's laws of planetary motion are laws describing the motions of the planets in the solar system. They were derived by the German astronomer Johannes Kepler. There are 3 laws of planetary motion. Let us talk about them one by one. Kepler's first law of planetary motion, sometimes referred to as the laws of ellipses, can be stated as all planets move about the Sun in elliptical orbits, having the Sun as one of the foci. This means that planets are orbiting the Sun in a path described as an ellipse. This is a picture of an ellipse. Suppose this ellipse is where the planet Earth moves. The Earth moves along the ellipse around the Sun. The Sun is located at either one of foci of the ellipse. Now let us move on to the second law. Kepler's second law of planetary motion, sometimes referred to as the law of equal areas, can be stated as a radius vector joining any planet to the Sun sweeps out equal areas in equal lengths of time. The second law describes the speed at which any given planet will move while orbiting the Sun. Note that when a planet is close to the Sun, it moves fast, but when a planet is far from the Sun, it moves slowly. So if we draw an imaginary line of the movement of the planet and the Sun for every month of the year, we can see that when the planet is close to the Sun, it will form a wide but short triangle, and when the planet is far from the Sun, it will form a thin but long triangle. The Earth would have to adjust its movements in order to match the imaginary area. Did you know that the knowledge of Kepler's second law has proved the importance of Newton's law of gravitation? Newton showed that the motion of bodies subject to central gravitational force does not always follow the elliptical orbits as specified by the first law of Kepler, but instead, planets or other heavenly bodies can take paths defined by other open conic curves. Amazing, right? Now let us move on to the Kepler's planetary motion, sometimes referred to as the law of harmonies, can be stated as the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distances from the Sun. It compares the orbital period and radius of orbit of a planet to those of other planets. It is the ratio of the squares of the periods to the cubes of their average distances from the Sun is the same for every one of the planets. The comparison of each planet can be shown in this illustration. Now, what does that mean? Kepler's third law means how long a planet takes to go around the Sun, which is its period, is related to the planet's mean distance from the Sun. That is, the square of the period divided by the cube of the mean distance is equal to a constant. And for every planet, no matter what its period or distance, t squared over r cubed is the same number. And that's it.
So the study of planetary motion was greatly advanced by Kepler, who deduced 3 laws that provide a mathematical basis for this motion. So here is the summary of Kepler's 3 laws. We have law number 1. Planets move around the Sun in elliptical paths with the Sun at one focus of the ellipse. We have law number 2. While orbiting a planet, sweep out areas in equal times. We have law number 3. The square of a planet's period, or the revolution time, is proportional to the cube of its mean distance from the Sun. And we have the formula, which is t squared or r cubed. These laws apply to any satellites orbiting a much larger body. So kanina formula is pwede magamit sa tanan nga planets basta lang makuha ilaha distance sa sun. So mura to guys, thank you.